I want to calculate the Coulomb energy term. You know, in the case of liquid drop model, we have many terms or many factors can affect the value of the binding energy. One of these terms is the Coulomb term, okay, which is equal to B Coulomb equals to AC times Z squared divided by A power 1 over 3. We need to calculate this term. Let me explain the situation in general. Inside the nucleus, we have a positive protons. In this case, we have a repulsive Coulomb force between them. This repulsive force will decrease the general binding energy of the system. This decreasing of energy equals to the electrostatic potential energy of this object, of this nucleus. Okay? So, the Coulomb energy term, we can say B Coulomb equals to the potential energy of this system of nucleus, of this quantity of charge. We can say PE or we can say U. Okay? So to calculate the Coulomb energy term, we have to calculate the potential energy of the uniform charged sphere. Here we deal with a problem in electromagnetism. Let me explain the physical meaning of this term. In order to put a small charge Q in the space, we don't need any effort. We don't need any external agent, external work to put this charge, because we don't have another effect of the external medium. Okay? Here we have the shape of the nucleus, the final shape of the nucleus. But inside we have only one positive charge Q with a radius R. It's a spherical object. So no energy required to place this charge. Now I want to add or to bring a positive charge and put it around this charge. In order to add a shell of charge, we have a shell object of charge dq. In order to add this quantity of charge and put it beside q, we need an external work applied because we have two positive charges. To bring this one, we have to push it, to bring it with an external force. Okay? This force needed, this work, equals to d omega, equals to the electrostatic potential energy. I know this, I think. In the first year, you know the work applied to any charge to put it in any system equals to the delta potential energy, delta U. If we have one charge Q1, we have another one Q2, the potential energy of this system equals to K Q1 Q2 divided by the distance between them. Okay. So the potential energy of this system of Q and dq equals to K Q times dq divided by the distance between them. Okay. Now, to calculate the total energy to bring another shell bigger and bigger to cover the entire shape of the nucleus. So we can do the integration of d omega of du, and we integrate this value. To cover all, we can add another shell like this to arrive to the final shape of the nucleus. Okay? Here we can say, first of all, we have Q, and we have one shell of a charge dq. The electric potential energy d omega, okay, equals to k q dq divided by r, because this charge is placed at a distance r from the center of q. Now I want to calculate q and the dq first of all, but before, you know, the final shape of the nucleus is a spherical object, has a charge capital Q. As we have a volume charge density of this object equals to rho, in this case, Q total of the nucleus equals to the volume charge density rho times the volume of the nucleus, okay, which is equal to 4 divided by 3 pi r cube. You know, r cube of capital R is the total radius of the nucleus. Why I use this relation? Just to calculate the value of the volume charge density. And later you can use this rho to find small q and dq. Let me calculate also the charge q, you know, here of this one. You know, this small charge and the dq in the total nucleus have the same volume charge density rho. So the capital Q equals to rho times the total volume of the nucleus. The small q equals to the volume charge density times the volume of this charge q, which is equal, here we can say we have a mistake. Let me solve the mistake and we come back. So here we put the value of rho equals to q divided by 4 over 3 pi r cube, and this is rho times the volume of this small charge, which is equal 4 divided by 3 pi times small r cube, okay, the volume of this one, okay. So finally we can eliminate here 4 and 4, 3 and 3, pi and pi. We get finally q times r small r cube divided by capital R cube. This is the value of q. And now I want to calculate dq. Also, we can follow the same method. You know, dq equals to the volume charge density times the volume of the shell, the volume of this shell. You know, the volume of any shell equals equal to the internal surface of this shell times the thickness, okay. The internal surface here of the shell equals to 4 pi r square times the thickness dr, okay. And we substitute the value of rho here, equals to, you know, here we can put 3 up. We get 3q divided by 4 pi r cube times dv. We can simplify this one. Anyway, here we put dq and the q here. D omega equals to here we have q divided by r, okay, times q times dq, okay. Q k divided by r, small q equals to capital Q r cube divided by r cube times dq, it's here dq, okay. We can simplify this one. We have here r cube and r, no, here we have r cube times r square equals to r power 5, and here we have 1, so we have r power 4. K, here we have k, capital Q times capital Q equals to q square, 3. Here we can eliminate 4 pi and 4 pi, and r cube times r cube equals to r6 times dr, okay. Now to calculate the total work applied, we have to integrate d omega equals to the integration of this term, okay. So omega, the integration of omega equals the integration of d omega equals to omega equals to the integration of this term. You know, here this one is constant, k is constant, q square is constant. You know, the total charge of the nucleus equals to q. It's a constant value. The radius of the total nucleus is constant. So we get only inside r 4 times dr, okay. It's the only variable small r. Here you have a integration between r equals to 0 to capital R to cover the entire volume of the nucleus. So it's very important, the limit of this integral between 0 and capital R. The integration of R4 equals to R5 divided by 5 between, anyway, this is the final answer. You get finally omega equals to 3k q square divided by 5r. This is the total potential energy of the total work needed to construct or to form this nucleus by the positive charges, okay, protons. This is the final answer. You know, let me simplify here. You know, Q, the nucleus is positively charged. Inside the nucleus, we have Z protons, and the charge of each proton equals to E. So Q equals to Z times E. This is the total charge of protons inside the nucleus. And you know the radius of the nucleus equals to R0 times A power 1 divided by 3. We substitute the value of R here, and Q equals to ZE. We get finally, let's say here, we get finally 3 divided by 5, K E square Z square divided by R0 A power 1 over 3. This value we can say equals to A Coulomb. You know K is a constant value, E is a constant value, and R0 is a constant value. So we can say we have A Coulomb, it's a constant coefficient of Coulomb term equals to AC. We can write finally omega equals to B Coulomb times AC times Z square divided by A power 1 over 3. Here I will do some simplification, okay? Because if you have Z equals to 1, in the case of one proton, in this case, we don't have any effect of Coulomb term, okay? It must be equals to 0. So we can write here this term B Coulomb equals to AC Z squared divided by A power 1 over 3. We can write it AC times Z minus 1 divided by A power 1 over 3. Nothing will change if we have a big value of protons inside the nucleus. Nothing will change. Z times Z minus 1 equals to Z squared. Okay, but in this case, if you have Z equals to 1, B Coulomb equals to 0. As we said, we don't have any repulsive forces in the case of one proton. So it's better to write this expression B Coulomb equals to AC Z minus 1 divided by A power 1 over 3. You can write like this, or we can say AC Z square divided by A power 1 over 3. Okay, the same notation. So before Q square, you can say Q equals to ZE, Q square equal to Z square times E square. Or you can write Q equals to Z minus 1. Okay, so no, you can say here, you can write equals to E square, this one, times Z square equals to Z minus 1. Okay, anyway, we can have Coulomb term will appear only if Z must be greater than to 1 in order to have two protons and we have a repulsive forces between them. So in general, you have to calculate this term if I ask you to find it. Let me explain one point. How can we profit from this term? In general, you have, we calculated B Coulomb equals to AC Z squared divided by this one. AC equals to 3K E squared divided by 5R0. From this expression, we can find R0. Okay? You know, in general, if I tell you calculate R0 directly without the calculation of AC, you can write directly AC equals to 3K E squared divided by 5 R0. We know the value of AC is given. You can calculate its value. I think it's 1.2 times 10 power minus 15 meter. Okay? If I ask you to find this expression, you have to follow all the steps to find this relation. You have to find B Coulomb. Okay? Maybe you can have some problem in the exam or in the TD to calculate B Coulomb in terms of AC. Or I ask you to find AC. I give you, for example, here, the value of R0 is given, and I ask you to find AC. You can write directly its value, or I can ask you to find it, and you follow the all steps to find this relation. Okay,